Good morning, everyone. We had almost finished with the air separation. We will conclude it in the first part of our lecture today, and then we will move on to water. Last time we went through the liquefaction of air and then the fractional distillation to recover oxygen. If you look at some of these plants, they are humongous. Like there's a plant in Qatar, you can see that this is the per day production of something close to about 30,000 tons per day of oxygen. You can imagine how massive it is and uh, how much air must be getting sucked into these systems. Sometimes I wonder, even with a very high capacity, but in the vicinity of these plants, there must be always a shortage of air. The rate at which air is getting sucked in. So it's really quite enormous. What we discussed last time is that the first approach that was taken by Linde, where the focus really was on recovering oxygen. It wasn't on nitrogen, but then because the nitrogen is also getting liquefied, and finally, if you're going to discard the nitrogen as waste, then obviously the incoming air, the cooling of that will be done by this nitrogen largely, and also by the oxygen which you are recovering in a gaseous form, not in a liquid oxygen form. So what will happen is that if your focus is only on standalone oxygen production, then of course the power requirement in the process would be much less, simply because you are utilizing the already cold and liquid form of discarded waste, the nitrogen, for doing the bulk of the cooling, and it's only the residual amount where you need to do the Joule-Thomson expansion, and obviously there's a lot of compression energy required for that. On the other hand, if you are trying to recover both nitrogen and oxygen, and especially if you are trying to recover it in liquid form, then there would not be that much of waste which is available to cool the incoming gases. Naturally, in that case, the energy consumption will be more because proportionately you have to do much more of the Joule-Thomson expansion to get to those cryogenic temperatures. But it is the air separation to get both nitrogen and oxygen, which obviously has been of great interest. As we discussed, the nitrogen which they had got previously was not very pure. So Linde kept working on it, and in 1910 he came up with an improved design. Now this is also very interesting, that please have a look that this is one great example where these people have actually applied hardcore chemical engineering principles to improve the entire process, and especially to recover both nitrogen and oxygen. What they have done is, it's very interesting. The boiling point intrinsically depends on the properties of nitrogen and oxygen, and we know that the boiling point of oxygen is higher than the boiling point of nitrogen when you are comparing it at the same pressure. Like let's say at 1 bar pressure, we know that oxygen will have a higher boiling point. But you could have an interesting situation where suppose, like let's say I take nitrogen at a higher pressure, so much so that the boiling point of nitrogen at that pressure is basically higher than the boiling point of oxygen at, let's say, 1 bar pressure. Now that's very interesting, because the nitrogen can actually transfer its heat to oxygen in liquid form. Okay? Because the boiling point of nitrogen is higher. Suppose I've kept it at a higher pressure. From these plots, you'll be able to make out, like this is the plot for nitrogen. This is the plot for oxygen. We're talking about pressure and temperature. So, like let's say if I keep my oxygen more or less close to about maybe slightly more than 1 bar pressure, maybe 1.5 bar pressure, you know, and at that temperature, if let's say this is my boiling point, okay, and now if I take nitrogen at let's say about 6 bar pressure, you can see that now the corresponding boiling point over here is higher than of oxygen. So nitrogen has a higher boiling point at 6 bar pressure than oxygen has at 1.5 bar pressure. This is the wonderful thing that he conceptualized, and you can see it's just based on fundamental relationship of boiling point with pressure. And so what he did was something extremely interesting. What he did was he actually took 2 columns. This is the high pressure column and this is the low pressure column. So this column is around 5 to 6 bar pressure, and this one is at about maybe 1.5 bar pressure. Now this part, whatever he's doing is identical. He's taking in air and he's purifying it, and then wherever you have got cold exhaust, where let's say liquid has to be converted into a gas. So wherever I can transfer the heat from the incoming stream to this, that's what he's doing. So that part is not very different. Now he's feeding, this stream after the Joule-Thomson expansion into the high pressure column. Okay. Now in the high pressure column, what's happening is obviously, see, once I'm at a high pressure, at that pressure, like over here, obviously oxygen would have a much higher boiling point than nitrogen over here. So what you will have is that you will have predominantly oxygen, which will be at the bottom, liquefied, and closer to the top, you'll have more nitrogen, naturally, because nitrogen has a lower boiling point than oxygen. And then what he's doing is, so this is predominantly oxygen, but not entirely. There will be, of course, some amount of nitrogen, because I'm not really doing a complete separation here. Then what he's doing is that he's taking this, and with the help of an expansion valve, he's feeding it over here into the low pressure column over here. Now, obviously, when I'm doing the expansion, there would also be a cooling that would take place, and so this will reach a lower temperature because of the expansion that I am doing, and I do need to cool it because I'm now going to operate this at a relatively lower pressure of 1.5 bar. So obviously, to liquefy something, you will need to have a lower temperature, and that is very cleverly done with the help of this expansion valve. Now what happens is something very interesting. In both the cases, what you are having is that you'll have oxygen towards the bottom of the column, and you'll have nitrogen towards the top. Here again, the same, oxygen towards the bottom and nitrogen towards the top. Now, but what happens is that over here, I have a very interesting situation where this oxygen is, as I said, at a lower temperature than the nitrogen vapors. Okay. So what will happen is that the nitrogen now will transfer its heat to the oxygen, and it will in turn get condensed and become liquid. So I have liquid at the top of the column also. And this thing over here is very interesting, that a single unit is basically serving both as a reboiler and a condenser. Reboiler for the oxygen which is going to volatilize because of the heat that it takes in from the nitrogen, and the condenser because in the process of transferring heat to the oxygen, the nitrogen gets liquefied. So it's really very interesting. They're forming liquid nitrogen here, and because you've got a fractionation column, so this nitrogen is a very pure nitrogen, because you can imagine that there is a very large difference in the boiling points of nitrogen and oxygen in the high pressure column. You can see, in fact, it widens. So you get very pure nitrogen over here in a liquid form. Now, what they do is you can either drop that nitrogen as a liquid nitrogen, or part of it you may also want to take it into the top part of the low pressure column, and it effectively does two things. One is that it will be at a very low temperature. So what will happen is that it will allow for the rapid liquefaction of the oxygen because the temperature is low, and in turn, of course, it will become a gas. So what I do is that I am doing a separation again over here, but this time what I'm doing is, from the top of the column, I am now collecting gaseous nitrogen. This is the part which is giving me liquid nitrogen, and this is the part which is giving me gaseous nitrogen. Of course, when I take it through this heat exchanger, one is that I do some heat exchange over here along with this stream before the expansion, and then again I do a heat exchange after the exit of the nitrogen from here, and all of those are what is cooling the incoming stream, and then later on, of course, finally I'm doing a Joule-Thomson expansion. So this is what they were able to do to simultaneously get both very pure oxygen and very pure nitrogen. And you can see because over here I'll get the oxygen as a liquid. So I'm taking out the liquid oxygen from here, and this basically, the crude liquid oxygen here is effectively going into the top column, and that's where the complete rectification and recovery of pure oxygen is taking place. This is basically the Linde double column system. Let me read out what it says. In 1910, the Linde double column system was introduced to overcome the limitations of the single column process. Two stacked columns are used in the system, each operating at a different pressure with a single reboiler condenser heat exchanger between the two columns. This is what it is. This is the great innovation. The upper column is the low pressure column, which operates at slightly above 1 bar within, let's say, 14.5 psig. The bottom high pressure column operates at about 5 bar pressure, 5 to 6 bar. The boiling point of pure oxygen at 1 bar is approximately 3 degree Kelvin below the boiling point of pure nitrogen at 5 bar. Look at how beautiful it is. This temperature difference allows the use of a single heat exchanger between the two columns, which serves double duty as a nitrogen condenser and oxygen reboiler. It is just amazing. And this is really what is the technology even today. This is what people do. Maybe they'll fine tune, some of the pressures, etc. Of the systems. And of course, operation would also depend on how much of liquid nitrogen and oxygen you want, how much of heat you want in a gaseous form. All of those finally will decide what will be my energy requirement in the system. Naturally, if I have got both of these as liquid, they're gone. I can't recover that. Okay, I can't cool this incoming air with these streams because those are being drawn off as liquids. So I can only do it from this stream which is going into the top column and the nitrogen which is coming out from here. That's it. That's what I can do.
I had a small doubt, sir.
Yeah, yeah,
Sorry to interrupt you. Expansion valve D1.
yeah, over here.
Yes, sir.
Yeah,
After that is passed, the oxygen, is that liquid oxygen below?
yeah, yeah. There will be, it will be partly liquid and partly vapor.
So, but why will there be liquid oxygen both in both the columns, like where the pressure is
Yeah,
1.5 bar
yeah.
as well as a
Because
6.5
you
bar?
see, it doesn't matter which column, whether it's this column or this column, the oxygen will always be at the bottom.
Why so, sir?
Remember that for both these columns, you have to compare like for like. So if you're comparing here, you can see that over here, boiling point of nitrogen is lower than the boiling point of oxygen. At 5 bar pressure also is the same. Boiling point of nitrogen will be lower than the boiling point of oxygen at that pressure.
Right.
Okay.
Yes, sir.
All right. So is that clear now?
Yes.
This was the revolution which really allowed for not only the recovery of pure oxygen but pure nitrogen.
Sir, the oxygen which we are getting is a liquid or a gas, sir?
Liquid, liquid. L stands for liquid. Okay.
Sir,
Because
then why is it written that two columns which serve double duty as a nitrogen condenser and a oxygen reboiler?
yeah, you see, what are you doing? You are also setting up a reflux here. So effectively, the liquid oxygen will also vaporize and it will reach a equilibrium with the nitrogen. So that way the nitrogen will continuously travel towards the top and the oxygen will go towards the bottom. A reboiler means what? What is happening in a deflux process? Things are volatilizing, going to the top, again condensing, coming down. That's what is happening. And that's how you are having a continuous exchange between the vapors and the liquid. And in the process, the liquid is getting purer and purer in oxygen, and the vapor is getting purer and purer in nitrogen. So I need to have a continuous reflux of this oxygen. That
Yes,
is
sir.
what is being provided, that heat, by the nitrogen over here.
Okay, sir.
Okay. Is that clear now?
Yes, sir.
Okay. And you can see again, this is a plant. I mean, look at the capacity for nitrogen. They're saying nitrogen, but I presume these plants also produce oxygen. It must be. They can't be, or it may be that they are, if they only have a requirement of nitrogen, then of course they will use the liquid oxygen to minimize the power requirement for Joule-Thomson expansion. I mean, for the compression preceding the Joule-Thomson expansion. That's what they'll do. But this is a plant which produces 50,000 tons of nitrogen per day in Mexico. Mind-boggling. Look at these units. So this is one of the really great revolutions, and hardly surprising that very soon after Linde developed it, he was awarded the Nobel Prize. If you look at the entire thing, that who would have imagined that air can be separated out cryogenically into nitrogen and oxygen? Of course, the larger credit in some ways must go to Joule and Thomson for finding out the Joule-Thomson effect, which is at the heart of it. Otherwise, it would never have happened. Okay? But then, even if they had done it, it was really Linde who excelled in this engineering, which enabled this to happen. So it's not very different if you look at it the way Solvay was a great engineer, and he did not really discover the Solvay process. I mean, it was done by others, but the engineering feat which he achieved enabled it to become a practical process. And likewise, the engineering feat of Linde is what really enabled him to make the Joule-Thomson effect and liquefaction of air then into something that he could help to or utilize to separate out oxygen and nitrogen. If my objective is only to recover oxygen, then of course I can use the liquid nitrogen to greatly reduce the power consumption for compression, because a lot of the cooling is going to be done by the waste liquefied nitrogen. and the cold nitrogen streams. Okay. But if I am recovering both oxygen and nitrogen, and I presume that's what this data is all about, it's just that 1 ton oxygen is shown as the basis. But you can see that the air requirement for 1 ton is 3600 normal meter cube. You can work out that you're talking about, let's say, 22.4 liters will have 1/5 of a mole of oxygen, which means it will be 32 divided by 5, roughly about 6 grams or so. So 6 grams per 22.4 liters, and per m cube, that will be about 267.85 grams. So 3600, now if I take, so 267 gram multiplied by 3600, yeah, it comes to about 964 kg of oxygen. So you can see that we are talking about virtually quantitative recovery of oxygen from the amount of air that you are drawing in. It's just spectacular. Please work it out yourself. Correspondingly, of course, you will get roughly about 4 tons of nitrogen, and your cooling water requirement is given. You remember the cooling water with which initially, after the compression of the air, we have to have cooling water to first draw off the heat before you do the further cooling. And the power requirement for the compression and for everything else, pumping and things like that, comes to roughly about half a unit per kg. You can think of it. Okay? So it's roughly about 450 to 480 kilowatt hour per ton of oxygen. You have seen the capacities of plants, but actually you can see that in some of these cases, they're talking about plants which are far, far bigger. What we saw in the Mexican plant and the Middle East plant. Is the calculation of the mass balance clear?
Yes, sir.
Okay. A lot of these plants, they also recover argon. Where will the argon be in this particular column? You remember argon has a boiling point close to oxygen. So where will the argon be mainly?
Bottom.
Like oxygen, so it will be also mostly liquefied, and it will be at the bottom. And so I am drawing the stuff from here and taking it to the top. So the argon along with the oxygen will be moved to the top column, because the boiling points of argon and oxygen are quite comparable. Very, very tiny difference. Clear or not?
Yes, sir.
Okay. And then over here, where will it be? Oxygen is at the bottom of the top column. Nitrogen is more at the top of the top column. Argon naturally will be in between. So you will draw argon from somewhere towards the middle of the column. That will, of course, depend precisely on what is the interior design of the column. There are many other factors. It may not be exactly in the middle. It will depend on a lot of things. But typically, you can have an argon concentration which goes up from 1% to something like 10%. Roughly from 1% in air. So in the belly of the top column, it can achieve something like about 10%. So what they do is that they take that mixture from here, which will have all three. There will be oxygen, there will be argon, there will be also some amount of nitrogen, which will go. Now, in this column, in the first column, what they do is that they recover the argon as a gas. And the temperatures are designed such that the oxygen is recovered in a liquid form. So the oxygen which is coming out over here at the bottom, oxygen will, because oxygen has still a higher boiling point than argon, so it will be at the bottom. So this oxygen is again being fed back into this column, and the argon will be largely free of oxygen, but there will also be some amount of nitrogen vapors which would have come into this column. So it will largely be nitrogen and argon with a small amount of oxygen. The separation in this column is so good that the oxygen and the nitrogen contents are very low. Oxygen is less than 1 ppm and nitrogen is about 0.5%. Then it is fed to a second rectification column. Now in this column they do exactly the opposite. What they do is that they recover the argon as a liquid and the nitrogen then comes up as a vapor. You take out the liquid argon from the bottom and look at the purity that it's able to achieve. It's 99.999% purity. So this is the way in which this argon is recovered. What makes it possible? Because the boiling point differences, especially between the oxygen and the argon, is not very high, as we had seen last time. So what they have is, instead of the sieve trays which I showed you, they have packed columns. You know, there are these are known as structured columns. I hope that when you all are studying these separation principles in more detail, that someone will discuss this with you. But in these columns, basically what they do is that they are able to minimize the pressure drop in these columns. And the second is they are able to maximize the contact area between the vapor and the liquid. Because that's what I need. I need to basically maximize my contact area so that I reach equilibrium more efficiently between the vapor and the liquid. So this is the kind of column which was introduced, you can see, in the mid-80s. And it is basically these kinds of things which are the basis of, for example, recovery of argon. Otherwise, it would have been very difficult to recover or separate out argon from oxygen. But it is these packings which do the job. This is from the Linde brochure. I'll pass it on to you if I've not done so already. Many of these things would be like incremental innovations. But the fact of the matter is that starting from 1902, and you see it goes up to 2017, every few years, they've had some milestone. Some of the milestones are basically related to scale, you know, that they have been able to put up plants with a gigantic scale. But some of these other ones are related to efficiency, selectivity of separation, etc. And you may want to have a look at it. But this is what research and development is all about. That continuously you see how to improve something. Otherwise, you know, if you're learning the subject as if everything is all done and there's nothing more to do, then there's no point in doing anything, learning anything. It's all that you learn it with an understanding that, yes, perhaps I can add to it and make it better. You know.
So just one thought.
Yeah.
In the Solvay process,
Yeah.
in carbonation tower, we were using mushroom structures, right?
Yes.
So is that also a part of structural packings?
Absolutely. Those are all types of, you know, only thing is that over here, probably you'll have a much more dense packing. You understood?
Yes, sir.
The packing will be far more dense because the kind of surface area that you require here, the two problems are in that sense almost an order of magnitude different in complexity. You know? Because you're talking about such small differences in boiling point. Okay?
Yes, sir. Thank you, sir.
Very good question, though. In fact, I have not gone into the details of packing, firstly because I myself don't understand these in depth, but I hope that you all will be able to study these over the next couple of years and become masters of it. Okay, now you've seen air and the great accomplishment of engineers in air separation. Now let us look at water. Okay? And water is, again, as you know, what double duty. It does triple, four times duty. It does so many things. It serves as a medium for reactions. You use it for as a cooling agent. You name it. You can use it for supply of heat by converting it into steam. And so water has such a phenomenal role to play again in industry. Now I know that most of you in your school would have been exposed to some of the properties of water, if not all the properties of water. But it is very interesting that when you are going, let's say from you can see what's the boiling point going from sulfide to selenite to telluride. You can see what's happening, and then you come to water. It's got a boiling point of 100 degree centigrade. It's just a massive change, which is taking place. And why does it happen? What is the reason why water behaves so anomalously?
So hydrogen bonding.
Absolutely, hydrogen bonding. You later on realize that the tremendous importance of weak interactions. We have seen weak interactions, how it came into the liquefaction of air, and how you did an adiabatic process and got a liquid from the gas. Likewise here, another weak interaction, but not so weak. Okay? And it causes such massive differences, that the bonds are so strong that rupturing those bonds takes a lot of energy, which is the reason why the boiling point is so high. And not only that, the latent heat of vaporization is so high. Okay? So that's very important. Now, you also look at another extremely important property of water, which is that it has got a fairly good thermal conductivity. Where do I need thermal conductivity? In which application? Where does thermal conductivity help?
So water jackets.
Absolutely. Water jackets, where I have to do heat exchanges. If I did not have a good thermal conductivity, obviously there would not be any efficient exchange of heat. Now, this is a property we will not be utilizing much, but let me tell you that it is extremely important to know the refractive index of water. For example, there's a process, and in fact, someone had asked me that how do I get some online device to measure impurities in water? And we are talking about impurities like DMF and things which remain from a membrane making process. It's so important that even traces of DMF alter the refractive index, and you can actually today have equipment where you can measure comfortably the refractive index up to 4 decimal point accuracy. These trace changes because of impurities, you will be able to actually monitor with refractive index. You can do that. Another very important property of water, as we know, is viscosity. What is viscosity exactly? What does it mean? Viscosity. What is viscosity due to?
So it is the obstruction offered to the flow of a fluid.
Absolutely, you're right. It's an obstruction. But it is an obstruction which is created by itself. In other words, if I look at, let's say, the flow liquid in a pipe. Now I can look at layers and layers of water, and if, for example, one layer of water is not able to slide past the other layer of water, the adjacent layer of water, and which can happen because of frictional forces. So basically, that is the obstruction that it is creating. It's not an obstruction created by anything else. It's intrinsically creating an obstruction for itself merely because one layer flowing with respect to the other is causing friction. And so that is the kind of frictional force. And so the frictional force per unit area is a very important aspect of viscosity. The second is also that the velocity gradient, like let's say in flow, can vary. Like for example, if I take the distance from let's say the wall of a pipe, towards the bulk of the liquid, and then I measure the velocity gradient of that, which is basically the change in velocity as a function of the distance z from let's say the pipe. That would have a overall unit of let's say meter per second divided by meter. So it will be per second, and this will have the unit of Pascal. So per second goes to the top, it becomes second, and so you've got your unit of Pascal second. Look at dipole moment, it's got a very high dipole moment. Individual bond moments are about 1.5 divide, and the net dipole moment of water is 1.85. Why is the dipole moment not 0?
Sir, because it is an angular molecule.
Brilliant. Angular molecule. Okay, so basically this is really the resultant of the two. You look at the heat capacity. It's got a very high heat capacity. It's important because it is really when you're looking at water as let's say a cooling medium, or if you're looking at it even as a heating fluid, it is the high heat capacity which is so important that you can do a relatively high level of cooling with relatively small amount of water. So if you look at all the things where heat exchange is so important, the specific heat is very important, and the thermal conductivity of water is extremely important. Okay. I did not also mention the surface tension. As you know, this is extremely important to know that the surface tension of water is very high. That again is something that one needs to look at, especially for example when you are trying to form an immersion and you have to lower the surface tension and to be able to form an immersion. Okay, so there are many important things related to surface tension. Also, water it's not a high electrical resistivity. It's quite low. It's about 18.2 mega ohm centimeter is the resistivity. Why does water have some electrical conductivity?
So due to the hydronium ions present.
Brilliant. Because there is a finite amount of dissociation. And that we know is your Kw. Now let us look at some properties. Some of them you will know very well, and but some of them will come to you as it could come as a bit of a surprise. Okay. One of the things about water that we know is that it has got an anomalous behavior around 4 degrees centigrade, where the density is is highest, and then after that, as you start cooling it more and more, and ultimately form ice, the density actually goes down. Okay? And so much so that ice floats on water, which is not something that one would have normally expected in many other cases. You would have probably expected that in the solid state it would have had the highest density. Why does ice have a relatively lower density?
So due to the structure of ice, sir.
Brilliant. Has a looser structure. It cannot actually form the hydrogen bonds as effectively in the solid. Okay? I mean, it does, but it has a relatively more open structure than in the liquid. Now, this is also what is the latent heat of vaporization of water?
Around 500.
Around 540.
540,
right?
yes.
540, sir.
540 kcal per kilogram, right?
Yes. Yes, sir.
And does this remain constant?
It changes, sir. It is at 100-degree temperature, sir.
And what happens if I increase the temperature or decrease the temperature?
It becomes slow, sir, when we increase the temperature.
It becomes?
Low, means below 540.
Okay. So let us look at the plot. This is the latent heat molar enthalpy. So this is your melting point and this is your boiling point. The latent heat of vaporization does not remain constant and it keeps going down. So if you come to something like the critical temperature, you'd be at about, what you can see is that the heat of vaporization decreases dramatically and goes almost to zero. So it's not something which is remaining constant. What is this latent heat? A lot of it is to rupture the hydrogen bonds. If I don't break the hydrogen bonds, it can't boil. When you are at these higher temperatures, it is like as if the hydrogen bonds are all broken up. And so I don't really need that much of heat of vaporization anymore. Just keep that in mind. Let us also look at, of course, again, something that all of you are familiar with. This is the triple point of water where the solid, liquid, and vapors can coexist. And then if we go higher in temperature, there's of course a rise in pressure as well, and there's a rise in temperature. And we are over here at the liquid vapor domain. And this is the point at which the liquid and the vapor become indistinguishable. They have the same density. And so you really cannot tell one from the other. It doesn't mean that there's no liquid, okay? But it is just that they are indistinguishable. And that's the critical point. It becomes a single phase. And if I go still beyond the critical point, then I really touch the supercritical temperatures. And so you can see the critical point is around 350, 370 degree centigrade. This is very important. We need to understand that under what temperatures and pressures you will have different behaviors. Now, what is very interesting is that as you go towards the critical point from, let's say, about 0 degree centigrade, okay, what happens is you can see the normal Kw, which we know the pKw is 14. That's what we have learned. But the pKw actually changes, right? And it tends to have a value which is lowest is at around 250 degrees centigrade. 250 degrees centigrade is here. So near the critical point, but it is below the critical point. Below the critical point, the pKw becomes lower. So if the pKw becomes lower, what does it mean?
More ions will be formed.
Absolutely, more ions will be formed. So let us put it down. Maximum dissociation. Okay, that's what you have at this point, right? So this is the point where you have maximum dissociation. After that, the pKw again increases, but even at the critical point, you can see that the value is about around 12. It's not 14. Okay? So what it means is that in this domain over here, what you have is the water itself can act as an acid and base at this point, and it just becomes more acidic or more basic. Okay? So you may be able to carry out some reactions which normally require addition of some acid or base catalyst. You might be able to carry out under these conditions without adding any acid or base. That would be great, because you don't have to add it. In this region, of course, the pKw is again going up in the supercritical region, but what we have seen is that the heat of vaporization goes virtually to zero. Okay, so what does that mean? What will be its property now? You know, what happens is that when I have broken up all the hydrogen bonds, like in this supercritical state, and the heat of vaporization has gone to virtually zero, actually it will start behaving more like as if it's an organic solvent. And so it will have the ability to dissolve things which normally would not have been soluble in water. So that's again very interesting. Look at the vapor pressure, of water, going, let's say, from the low temperatures in Kelvin, from the triple point onwards. It's interesting that the vapor pressure climbs up exponentially. And you can see, I mean, if you make a logarithmic plot, it's absolute straight line. What a remarkable behavior of water, and how the vapor pressure is changing. Okay, so this again is something important for you to make a note of. Now, this is futuristic technology. This is the kind of thing maybe 10 to 20 years from now, you might find people talking about more. That is actually carrying out organic processes in these kinds of near critical and supercritical water. Like, for example, there are many reactions which have been carried out, actual chemical synthesis under these conditions, where really what you are taking advantage of is the higher acidity and alkalinity of the water under those conditions. So many of the things which are normally you might associate with acid catalysis, like hydration, dehydration, elimination, hydrolysis, you can actually carry it out in supercritical water without putting any chemicals in, such of that kind. Now, there's another class of reactions which have been looked at, which is that, like for example, today with all this plastics, etc., we are talking about how to degrade the plastics, maybe convert them into fuel. Look at this. I mean, you can actually take rubber tire, in supercritical water, and it has been converted into oil with a 44% yield. Not bad. Supercritical water is actually also used to extract out more of oil from these oil shales. So that's again quite an interesting application. So lots of different reactions you might be able to look at, and also the rate of the reaction typically tends to be much faster under those conditions. And you don't have this hassle of if you have to use a catalyst, and again, how will I get rid of the catalyst? You don't need anything. You just need to drop the temperature and go from supercritical to normal conditions and work up your reaction. Like whatever was soluble in water will again become insoluble in water once I go back to the normal state, and it's very easy to work up. I can do it. The penalty, what is the penalty in all this?
So greater energy.
Absolutely. No free lunch. Penalty, energy required. This is again, another, sometimes it becomes really a problem to deal with some waste. The beauty is, like, let's say if I'm having an effluent discharge in water, already it's in water. Now, if I can bring it to the supercritical state, of course, granted that there would be a huge energy requirement, but if I could have, there would be huge advantages. One, as you can see, that most organic compounds become completely miscible with supercritical water. Second, oxygen solubility, which is not so high in regular water. Oxygen is freely soluble in supercritical water. And so what happens is that after all, when we do all these biological or chemical oxidation to convert all organics in effluent into carbon dioxide, I need oxygen, right? I can promote a more efficient reaction simply because I've got such a high concentration of oxygen. Otherwise, what happens is that my impurities are also at a low concentration, my oxygen is also at a low concentration. Naturally, my rate of the reaction will be sluggish. Okay? But at least if one of them, I can increase its concentration to a very high level, then at least one of the constraints is lifted. The third, of course, again, a very important point is that merely because I have reached such a high temperature, the supercritical temperature, naturally it's easy to overcome the activation barrier of reaction because of the Arrhenius equation. So because I'm at such a high temperature. So you can actually carry out many of these degradation of wastes in aqueous effluents in a matter of minutes. So this would be something to look at. I always tell people, yes, it is true that it is very, very energy intensive today. But suppose, like let's say 30, 40 years from now, that constraint is lifted, and let's say there is abundant energy from nuclear fusion, then generating energy may not be an issue. Then maybe these would be the ideal technologies to adopt. Okay? And I'm talking about things like fusion where I don't have a carbon footprint for my energy generation. So if under those conditions, in the future, if that happens, if fusion becomes a reality, then I mean there's absolutely no reason why I will not start looking at all these as possible reactions. So keep that in mind. Now let me take you to the book of Dryden and tell you about that water is becoming a very, very serious issue in our country. Remarkably, in 1968, when Dryden wrote this book, even at that time, they were concerned about water. So it's not as if the shortage of water is necessarily something which has happened only today. It's always been there. The problem may have got aggravated in recent years, and we will discuss why. But what he says is that he's trying to give what are some of the factors responsible for water shortages. And such a visionary man. I mean, at that time, the beautiful way in which he articulated all this. And mind you, he came to us from the United States. He was doing a sabbatical in IIT Kanpur, and that's where he wrote this book, around 68. And very nicely, he pointed out many things. One, he said, which is so important and is becoming increasingly important, that we have not been able to, he says, failure to provide equalization of surface water runoff. In other words, what is happening? We get lots of rain, but all that rain, when I'm saying all that rain, I'm exaggerating, but most of it finally finds its way into the sea, right? And increasingly, the problem is getting worse because of ever more deforestation. There is earlier, we had a lot of forest cover, and water could had a residence time where it could sit in these long grasses and things and slowly have the time to percolate into the ground. That's not happening now, and a lot more water is just getting drained into the sea. In fact, just about a week back, I was in Karwar and saw the point where one of their rivers, the Kali River, meets the sea. I mean, it's such a interesting thing to actually see how the fresh water in that river is really finding its way into the sea. It's splendid. Okay? So it's a reality. Over concentration of population in industries. Oh, this is becoming a much more serious problem today. The population has surged in our country. Okay? And so obviously the demand for water has gone up. Okay? And what has happened is, of course, in some ways it's a good thing also, but there has been too much of a clustering of industries. So the local demand for water in certain pockets has increased a lot. So that's a big problem. Now, when all this pumping of water, there was a lot of subsidy given for pumps. People then merrily started drawing water from the groundwater and depleting our aquifers. The rate of charging of those aquifers was not so good, and it's become worse, as I said, simply because of deforestation. There is a net higher drawing of water from the groundwater. While it all looks nice and you get bumper crops, but people are not realizing that our posterity will pay the price, and our aquifers are getting depleted. There's a lot of water wastage. You'll find from leaks in pipes, etc. Water gets wasted. Now, when we are talking about water, we are really talking about fresh water. We know there is plenty of water in the sea, but that's not the water we are talking about. We're talking about fresh water. failure to use salt water in place of fresh water. There are so many plants along the coastal areas, power plants, industrial plants, lots of plants along the coast. But even they use fresh water, and they don't use seawater even for their cooling, etc. Why? Simply because of corrosion-related problems. Because at those temperatures, you cannot generate steam from seawater because it will completely corrode all your reactor and pipes and etc. I mean, so you need fresh water. Okay, so that's a problem. Although from a thermal conductivity point of view, the use of seawater would have been good because the thermal conductivity is even better. Okay? Poor selection of plant sites, the lack of industrial coordination. People are putting up plants where there is a shortage of water. Almost the same way that so much of agriculture of things like sugarcane, etc., is done in places where there is paucity of water. So that's a problem. Okay, and then inadequate design of water-consuming processes and equipment. You know? So this is an area which he says also needs to be looked at, how to improve the designs and of various kinds of things like even heat exchangers and things like that. And then he suggests steps to reduce industrial water intake. Obviously, most important is to reuse water, but very practically wherever conditions permit. You know? So, but it would be so naive and so stupid to chuck it away if it could be reused, or if it could be reused with some minimal treatment. Now, using cooling water in series operations, adiabatically cool and reuse, obviously where you are using water to cool reactions and the water is getting hot, you don't go and chuck away the whole water simply because your water has gone hot. So you obviously will try and find clever ways of trying to cool the water back. And so we will look at, how people do that. The condensate, like for example, you're generating steam, you're from a boiler, and then when it's doing its job, the steam is becoming water. Don't throw away that water. Try to reuse that water. So recondition waste and wash water for reuse. He says, check the pressures on lines, etc., to make sure that there are no leaks. Keep heat transfer equipment clean. Because imagine if they are encrusted with salts, obviously, your heat transfer efficiency will go down, and you'll keep putting more and more water to do the same job. So obviously, keeping things clean is so important. You'll also find it is true. In many cases, what you find is that hot and cold water lines are almost adjacent to each other, and there is unnecessary radiative transfer of heat from one to the other, which is so stupid. So obviously, you should try and insulate those lines so that there is no such wastage that takes place. And another very interesting thing that he talks about is substitute air for water where possible. Is it possible? Let me ask you. Or substitute water with something else in any application that you can think of. Substitute or minimize, reduce.
Yes, sir. We can use ammonia and other substances as a coolant.
Yes, I mean that would be one way. Okay, that's good. That's good. Of course, you'll pay a price somewhere
Yes,
in
sir.
terms of the power cost. Nothing is for free, right?
Yes, sir.
Yeah, so I mean, it's not free, but anyway, I'll put it down. Substitute water with ammonia, etc., for cooling. Okay. What else? In fact, I don't know whether those cars still exist, But I know that one of my first cars in the US was a car which had an air-cooled engine. So you can use air for cooling. Air for cooling of engine. There are also very creative things where what do you see when you go to a toilet in the aeroplane? Is the flush different from the flush in our homes? Well, don't you see that it hardly uses any water? You press that button and there is a massive suction action, right? And all the dirt, everything goes with it. There are two things. Like, for example, the pan, the toilet bowl, has a Teflon coating so that things don't normally stick. Anytime you have to dislodge dirt, you have to put a lot of water. Okay, but if it doesn't stick, that's the first problem that you have solved. And then these planes, they create a vacuum, and with which they suck out all the stuff. I don't think the water amount would be not even 5% of what you would use in a regular toilet bowl, maybe 1%. And so that's another great example where you're using negative pressure to clean something. Those are all the ways in which you can do clever things and try to reduce water consumption. Draw inspiration from aeroplane toilet. Okay, this is not the only problem that we have today in our country. One is that there is a shortage of water. On top of that, the water quality is a huge problem in our country. In many parts of the country today, the water is brackish. You cannot, I'm not even talking about drinking water. The industrial water, you cannot use it. So people have to do a treatment. There's hardness, there's salinity, fluoride, nitrate, name it, pesticides. There are all kinds of junk in the water, and we have really messed it up over the last many years. We have just been callous and allowed all these impurities to get into the water. So quality is another huge issue. And so to first get a source of water, fresh water, which many times industries don't have, plus to treat the water so that it becomes of an acceptable quality. That can add very significantly to the cost of industrial operations. Now let us look at quickly one by one. Look at this study was done by one of the NASA satellites. It used to be called it was the GRACE satellite. I think it was around can't remember when, maybe around 2010 or 14 that they did this work. And they were able, it's something which is based on being able to measure very precisely subtle changes in gravitational pull at different places on the Earth, from which they were also able to compute what is happening to the aquifers, whether they are getting emptied out or not. Okay? One of the aquifers in the Indus Basin, our Indus Basin, was the third most severe problem, where they unambiguously established that by measuring things over many years, that the net withdrawal of water from the ground as compared to the amount of water that is being charged into the aquifer was positive. That means more water was being taken out from the aquifers. And this is reality today. Every day you go, you'll find people will say, I need to make my borewell deeper to take out water because all the shallow, the low-hanging fruits are all gone. And also because of this constant overdrawing of water and not getting charged, the quality of the water is also deteriorating. Because what is going into the water, into the ground, not necessarily very good water, but all the effluent, from agriculture, from industries, they are finding their way into the aquifers and they are contaminating the water. Now let us quickly look at what normally is believed, to be the overall water situation for an industry. What do? Most industries will take draw water from the municipal water or maybe from rivers, lakes, etc., next to which they are set up. Some of the water may need to be purified, so that is the demineralization process. And then and some of it you may not need to purify. So these are all your inputs of water into a chemical industry. And then what do you have? Well, you may require water for running your boiler, and then your boiler feed water you might be able to return into the chemical industry. Some of the waste steam condensate, the steam which condense to form water, that also goes here. Then if you use water, for example, cooling reactions, etc., you're in cooling operation and your water has got warm, if not the entire amount, quite a bit, the major fraction of the water you might be able to adiabatically cool and then recycle. Then sometimes water is produced in reactions. So that actually is not a water that you put in here, but you actually produced the water. So there is an opportunity of making use of such water, or if it cannot be used, then of course it goes off as waste. And then of course you can have water in your products. Like if I'm making an emulsion paint, what is an emulsion paint? Is basically beads of latex which are dispersed in water. So I have water in my product, and then I can generate wastewater. Out of that wastewater, I might be able to partly recycle some of the water and discharge the rest, or probably in the majority of places, they treat and chuck the most of it into the nala or river or whatever. So this is the overall picture of water. Let us look at quickly, let's take, for example, this process which is so important, especially for power plants, which consume massive amounts of water. Now, so what are we doing? You are actually generating a lot of hot water. Your water is getting heated, it's becoming steam, running your turbine, then it is condensing. It's still very hot water. I need to cool it. If you do it adiabatically, that is Q is equal to 0, what you have is that if you pass dry air, you take this hot water from your industries, or power plant, and you are pouring it from the top, and this is your cooling tower, and from the bottom you are passing dry air. When I say dry air, it could even be normal air. I am passing it. What will happen when I pass this dry air and I've got water coming from the top, hot water?
So the water will cool and air will get heated up.
Wonderful. Why will the air get heated up and why will the water get cooled?
Because air is at a lower temperature than water.
But what do you think is the heat capacity of air? It would be very low, right? Normal dry air.
Yes, sir.
Right. In which case then I would require tremendous amounts of air to carry out that cooling. But you see, what you take advantage of is the plot of the water in air. Grams of water per kilogram of air. So if let's say I'm starting with a dry air and let's say I'm having a temperature of around 30 degrees or thereabouts, I've got a certain amount of moisture content in that air. Now, when I'm passing this and when the water is falling from the water, what will happen is that a part of the water will vaporize and it will go along with the air. Why? Because it has got the capacity to take in a lot more moisture, and the latent heat which needs to be provided for the evaporation of this water, which finally finds its way along with the air, is coming from where? Where is the latent heat of vaporization coming from? It's coming from the water itself, no? So it's hot water. So the a part of the water is volatilizing, and for volatilizing it needs to carry the latent heat of vaporization, and that is bringing down the temperature of the rest of the water. And because the latent heat is much larger compared to the sensible heat, so with using a tiny amount of water which is lost in my air, a lot of water can be cooled. So that is the operating principle behind a cooling tower. Is that clear to everyone?
Yes, sir.
So just imagine the amount of water that can be recycled in this process. Let's take you through one more example and then we will close. We talked about also that that water can be produced in a reaction. For example, if you are operating a boiler and you are, let's say, using natural gas as your fuel, so what will happen? The natural gas is burning and it's forming carbon dioxide and water, and natural gas is quite pure, just methane. There's nothing else there. Whereas, if I had heated it up with coal or something, there would be a lot of impurities. But here it isn't, and quite a substantial amount of water is being formed. From 16 grams, I'm ending up getting 36 grams of water. Where is this water and all coming out? It's coming out in the flue gas, right? The carbon dioxide and the water and the remaining air and the nitrogen, that's all flue gas is coming out. Now, normally the flue gas is coming out at a very high temperature, and there is something known as an economizer, which is used to effectively extract the heat and really preheat the incoming feed stream that is going into my boiler for steam generation. You can even cool it down further. Normally people would come up to a temperature of say around 85-90 degrees centigrade of my flue gas through these steps. But if you're smart, you can actually cool it down further through what is known as a condensing boiler. And if you can come below the dew point, you can actually recover this water. So that is what a condensing boiler does, that it goes further down in temperature and it recovers this entire water. Now this company, Atul Industries, is actually operating this, and it even about 5 years back, it was saving something like 6 million liters of water every year. Plus, I save the heat because when it condenses, I get that latent heat back, right? The latent heat of vaporization I get back during condensation, and so I can again generate huge amounts of heat. And so this is the kind of smart thinking that helps, okay, to reduce the water consumption. And in
So,
this
but
case,
this can exclusively be used for or in industries where methane is produced, right?
absolute, but not produced, where it's consumed. You are using it as a fuel.
So basically, if you're consuming CH4, then a part of the consumption is transferred for water, for saving water, or
No. This though I'm burning so that my water can be converted into steam. No,
yes,
it's
sir.
a boiler.
So, but this is just a this is a side reaction in the entire industry, right?
No, it's not the side reaction. This is the reaction of the furnace. This is where I'm putting in natural gas. Okay? And this is an exothermic reaction, right?
Yes, sir.
So this is what is generating the heat, which is heating up the water for the boiler.
Okay.
Is that clear?
Yes, sir.
Huh? Okay. We will continue from here tomorrow. All clear so far?
Yes, sir.
Okay.
Thank you, sir.
Okay. Thank you.